Okay, so I make it slightly after 3 o'clock here in the UK, and would like to say a very warm welcome to everybody who's participating in this, the first of our series of Pico webinars. So thank you ever so much for joining. Welcome, and as I said, this is the first in a series of webinars that we're going to be running over the next 6 months as a minimum. So I hope that you find it useful and informative content. So before I hand over to the presenters, just a few housekeeping notes. So the webinar will last for approximately 45 minutes, and we intend then to have a questions and answers session at the end. So if you have questions that come up during the presentation, if you can post them please in the chat box that you'll all see at the bottom right hand side of your screen, that would be great. And then we, the presenters, and I will do our very best at the end to field those questions. So please do feel free to type them as we go. The webinar is being recorded, so we're recording the audio and video presentation streams, and it's going to be made available after the close of the webinar. So just to make you aware that that's going on. And everybody that's attending, apart from the host, which is myself, and the presenters, is muted and cameras are off by default. So the best way if you want to contact us is to use the chat facility. So moving on then to some very brief introductions. My name is Mike Purday. I am part of the distribution sales team here at Pico. Presenting the webinar is our business development manager, Trevor Smith, and he's being assisted by two members of our engineering team, Stuart and Patty. So Stuart will be giving a demonstration of CAN decoding, and Patty will be talking about the engineering and the science behind our BroadR-Reach solution. So, as I said, please, I hope you find it enjoyable content, and I'm going to hand over now to Trevor Smith, who is presenting and the content for the webinar. Trevor, your floor.
Thank you very much, Mike. So, as Mike has said, we've got about 45 minutes. We're looking at the evolution of CAN to BroadR-Reach networks, automotive networks. And I'll be assisted by Stuart Murlis and Patrycja Szelag at various points. So just to start things off, what I would like to say is a few words about the company for those of you who have not had any dealings with Pico Technology before. We're a UK company. We're headquartered in a small town called St. Neots, fairly close to the Cambridge University town. We were founded in 1991, so we've enjoyed, since that time, 29 years of continuous growth and counting. So financial year runs to the end of June, so we're hoping to make that 30 years in the next 6 months. We produce PC-based test and measurement equipment at fair prices. So we differentiate ourselves from other test and measurement companies in that we do not produce benchtop test equipment. We produce oscilloscopes, data loggers, RF test equipment, and the like, but it is all PC based. That is to say, it is connected. The test equipment is connected to a host computer, in most cases by a USB interface, in some cases a LAN interface, but in any case, there is always a PC that acts as the host. We have regional operations both in the United States, in a town called Tyler near Dallas in Texas, and an operation in Asia Pacific as well, with an office in Shanghai and staff in Tokyo. We have about 130 employees worldwide and global representation. We're represented in every country except Antarctica worldwide. So the agenda, we'll look first of all at the big picture, what's happening in the automotive industry, the megatrends. We'll look back a little bit to take a little bit of a historical perspective as to how network topologies have evolved and where they've got to date. Stuart will give us a look at our CAN bus debugging and analysis solution. We'll look at next generation networks, which is primarily BroadR-Reach, Ethernet 100 base T applications. We'll look at some of the capabilities we've got within our own BroadR-Reach solution that operates on the PicoScope 6000 E-series products. And then we'll have a demonstration of that, and we'll take questions, as Mike said, at the end. So the big picture, this report, it's a little bit dated now, and it's perhaps been affected a tad by the coronavirus since it was produced. But nevertheless, the automotive market is by any standards a huge market, and significant growth is expected in the next 10 years. And that growth is going to be driven by new technologies. So it is expected worldwide that by 2030, up to 70% of new cars that are sold will have self-driving features, and 15% of them could be fully autonomous. So autonomous driving technology has the potential to reduce holdups, dramatically improve road traffic flow, but also to save lives. There are currently around 1.35 million fatal road traffic accidents each year around the world, and actually more than 40,000 in the United States alone, according to insurance statistics. And most of those fatalities are due to human error. And the estimate is that around half of those could be avoided with driverless cars. So it's got the potential to save over 600,000 lives each year. And associated with that, it means that public safety expenditure could also drop. And the savings are estimated there worldwide at around $234 billion each year. So there is huge incentive to get this autonomy working well. Vehicles are being designed with increasing network connectivity. So direct data flow between cars and the wider infrastructure unlocks possibilities, including advanced driver assistance systems, diagnostics, analytical tools, enhanced safety features, real-time traffic updates, and rerouting and infotainment kind of applications. And then the third big driver is the switch to electric vehicles. It's very much underway. I'm the proud owner of a Tesla Model 3 myself, and I don't think I'll be going back to the internal combustion engine ever. Concerns over climate change have tightened environmental regulations worldwide. Many countries and major cities are aiming to put an end to petrol and diesel engine cars on the road. Another factor, perhaps a little bit less relevant to this afternoon's presentation, but urban populations are finding car ownership to be increasingly expensive and inefficient. So ride sharing and vehicle sharing are finding more support in the big cities. So vehicle manufacturers are having to invest and adapt in order to address those needs. But automotive networks in some way or other are integral to all four of those ACEs, megatrends, as we're calling them. Until the 1990s, each signal between a node or an ECU was sent across a dedicated cable, which made for point-to-point networks that linked all of the ECUs in a vehicle. However, it is easy to see from the illustration on the top right-hand side here that an ECU at any network needs to communicate to multiple ECUs. The cabling requirements rapidly escalate. So in this simple network of only 5 ECUs, there are 25 dedicated cables that are required to link them. So it rapidly becomes, it's not really a scalable way of building things. So the need to reduce the amount of wiring in vehicles led manufacturers in the late 80s, early 90s to develop in-vehicle buses where multiple cables are replaced by a single cable that may itself contain one or more individual wires. And data from different nodes on the network is serially multiplexed onto a single signal, which can then be transmitted on the one cable. One of the earliest and most widely deployed automotive serial bus networks is the CAN bus, or Controller Area Network, which was developed in the mid-1980s by Robert Bosch GmbH. And the intention was to develop a high-speed and reliable communication system between multiple ECUs, but one that was without the need for any host controller. CAN 2.0 was introduced in 1991 and was first implemented in production by Mercedes in the early 1990s. And it was ultimately standardized as ISO 11898 in 1993. Many different network protocol standards have emerged. Each one is designed to take advantage of emerging semiconductor technologies and optimized for some combination of communication speed, cost, the weight of the wiring in particular, robustness and reliability, so redundancy, and compatibility with previous generations. So there's a lot of design trade-offs that take place in the design of those, in the choice and the design of those networks. Unfortunately, ease of design debug is not usually high on the list of requirements. So it's tended to be true that each successive generation tends to be tougher to debug and requires more advanced tools. Vehicle networks, they obviously have to be designed and thoroughly simulated at every level. The hardware also needs to be thoroughly stress tested across worst case conditions to ensure the reliable operation once the vehicle is deployed in the market. Protocol analyzers like the CANU system from Vector Informatic are ideal for that function. And they can be configured with something called option.scope, which in fact is an OEM version of the PicoScope 5444D, to address every layer in the OSI stack. But what we're focusing on in this presentation is debug and analysis of the physical layer. In other words, the waveforms that make up the bits and the bytes of the data transmission. So what I'd like to do now is hand over to Stuart Murlis, who will give us a short demonstration of our CAN bus decoding capability on PicoScope.
Good afternoon, my name is Stuart Murlis, an FAE here at Pico Technology. In this demonstration, we are going to acquire and decode multiple frames of CAN data using the PicoScope 6 serial decoding tool, one of many protocols that is available as standard in the PicoScope 6 software. To set up, what I will do is go into my Tools menu and select Serial Decoding and then select Create. You'll see we have a series of standard serial protocols including BroadR-Reach, CAN and CAN-FD. Now if I had to go into my settings, you'll see my specific settings for this particular setup. The threshold, the hysteresis and the baud rate. As you can see on the screen, we have CAN high, and then we also have the darker purple trace is CAN low, and then of course we have the differential, both CAN and CAN low, the difference between CAN high and CAN low. Viewing the difference between the two removes any common mode interference encountered by the signal during transmission. Now, as you can see, we are decoding data and we can look through the coloured packets. So the orange, if I hover my mouse over the orange, you can see that's packet 5. That is the arbitration field. If I move over to the green, That's my control field, and of course we've got the data field, and right at the end of the frame we have our end of frame data. Going down into the table view, you can see we've got our identifier there, and we've also got our remote transmission request. We've also got our DLC code. So there are multiple information in tabular form available for you to look at through your serial decoding table view. Thank you very much for listening.
Yeah, thank you, Stuart. So that's an example of just how easy it is to see the frame contents and the decoded packets in a CAN bus communication using PicoScope. The point is here that correlation of the data in those packets to the signal that is being transmitted really is the key to being able to debug a network effectively. If you can see an error in terms of the data that's being transmitted and then correlate that to a signal integrity problem, a crosstalk, overshoot, rise time problem, or whatever it may be, race hazard or something like that, then the correlation of the two is what enables engineers to get to the root cause of problems in their networks as rapidly as possible. So that's CAN bus. It's very, very widely deployed in today's cars and continues to be. Of course, with CAN FD, there are faster versions of that. Looking forward at kind of to where we are and to where we're heading, the next generation of vehicles will undoubtedly process absolutely enormous amounts of data compared to what we've dealt with in the past. So I mentioned the Tesla, the one that there's a picture that I took yesterday morning as I was driving to the office here in St. Neots. So I had the auto drive on. It's not a great picture, unfortunately, but it was the best I could do while I was driving the car. But of course, I didn't need to spend too much time looking at where I was going because the car was doing a lot of the work for itself. So multiple cameras, radar, LiDAR, and numerous other sensors all have to be processed in order to deliver the promise of these driverless vehicles and today the advanced driver assistance systems. Vehicle to vehicle and vehicle to transport infrastructure communications is to come. So that's something that's very much on the horizon. And as I mentioned earlier, the cost and the weight of the vehicle harnesses is always an issue. Manufacturers are desperate to keep both the weight and the cost to a minimum. So the solution that has been broadly adopted across the industry is that of BroadR-Reach, and you can think of it as automotive Ethernet. So BroadR-Reach is now an open alliance. It's called the Open Alliance BroadR-Reach physical transceiver specification. It's been standardized as IEEE P802-3BW. So, and it's the one that we're looking at today is the 100 base T1 standard. So it benefits enormously from the economy of scale from technology that is already widely used in office and other networking applications. But it addresses the additional requirements in vehicles for hostile automotive applications, whilst meeting that requirement for low cost, low weight, using an unshielded, twisted pair copper cable. So the cable that it uses isn't the networking cable that you're familiar with in office applications. It's this thin pair of twisted copper cable that is used to transmit the signals. So the BroadR-Reach physical layer looks a bit like this. So we have the twisted pair cable that we can see and we can access. So if we want access to look at the signals that are going on the signal, then we've got points that we can readily access at the input and at the I/O of the transceiver at each end, and then there is the PHY, the physical layer part of the transceiver, and the MAC, which is effectively standard Ethernet MAC interface. Now the problem that we have is that, as I say, the networking doesn't look like this that you see top left, which is what you will have been familiar with using Cat5 cable in an office network. It is just a single twisted pair wire. So, and it's bidirectional, it's full duplex. So, and we don't normally have access to what's going on in here. So our test access points are here and here, but we need to know what's being transmitted in each direction to make sure that the transmissions are good. So we need some tools in order to achieve that. So what I'd like to do now is to introduce to you Patrycja Szelag, who will take us through some of the characteristics of the BroadR-Reach physical layer. Patty.
Thank you, Trevor. Hello, everyone. Yes, so before we can discuss BroadR-Reach decoder and the packet structure, I would like us to go through some signal characteristics to get familiar with, to know how did we actually get to the decoding data. So BroadR-Reach, as Trevor mentioned, is based on the 100 base TX decoder at Ethernet standard. Actually, it's 100 base T1. And this adaptation employs PAM3 encoding. PAM stands for pulse amplitude modulation, which means that the signal data, the signal values are encoded in numerous pulses, where in order to know the value of the sample, you would need to probe its amplitude. And PAM3, the second part, means that in PAM3, in this adaptation, we've got only 3 individual levels that the signal can get. So in here, we can see eye diagram, which is usually used for the intersymbol interference characteristics, finding the characteristics. And you can see 3 distinctive levels that the signal took, low or -1, middle, null, or and high, which is +1. So going forwards, we know that one symbol can take all these 3 different levels. So if we pair them together, so if we take 2 individual symbols and pair them together, we've got 3 times 3 number of combinations, which is 9. So a pair can encode 9 different possible combinations. So if we discard 1 just to get 8, which is 2 to the power of 3, that would mean that 3 different bits of the information can be encoded by 2 of the symbols. And that's basically how the packet is being decoded. Each symbol is transferred with 66.6 megahertz, so the pair would take 33.3 megahertz. So if you multiply it by 3, that is 100 megabits per second. So that's the speed of the transmission that PAM3 or BroadR-Reach can transmit. So it's good at like, why was it chosen to get implementation in the automotive industry? And that's because it can operate with a low quality cabling without compromising the filtering and the high levels of filtering, and also to provide improved emissions and noise immunity. Okay. So that's looking from single endpoint perspective. So each endpoint emits PAM3 signal. But because this is a full duplex decoder of full duplex transmission, bidirectional, all these PAM3 signals are adding up together. So in the end, if we were measuring the signal at one endpoint, this is more or less what we could see on the screen of the scope. So we've got here two channels. One was probing the signal at closer on the transmission line, closer to master, channel A on the top, and channel D on the bottom is closer to slave. And you can see that there's nothing that looks like PAM3 signal. It's more closer to PAM5. Obviously, it's not the same, but that information can't be decoded because you can't predict which combination was transmitted at a given time on the given sample. So usually how industry copes with that situations, that problem, they use what's called directional coupler. And on the right-hand side, we've got an example of Rosenberger solution. And that device is usually inserted in the system on the transmission line. And it allows to separate both endpoints communication in order for further inspection and investigation. Obviously, such solution interferes heavily with the system, produces bias, and that's not desirable. So our engineering team was kind of interested in, aside to creating a decoder, which we would deal with a PAM3 signal, could we actually also achieve a similar solution to this hardware directional coupler, but in the software. So first thing, and it's also visible on this graph on this picture, is that probing to different endpoints, you're just probing to the same communication. So basically you should see, if not identical, but very close to identical signal on both ends, right? Why is it so different? And that's what's called a velocity of propagation. Is a physics or electronics measure that defines a delay of a signal propagation in the cable relative to the speed of light in the vacuum. And we took that measurement and we thought, okay, maybe that's a key to developing a solution. And that's actually, after a couple of experimentation and a white paper that is going to be quoted later, employing also the spectrum analysis, we actually achieved a software directional coupler. And that solution is available for you in PicoScope 6, also in PicoScope 7, under math channels, and it should work, and it does work on any full duplex communication. So it's not bound to BroadR-Reach. You can use it on any full duplex bidirectional communication to separate out both channels. What obviously you need to have is these signals, so two probes that would probe the signal on two ends of the communication, or not even ends, like, you need to know the distance that the probes were inserted apart, because obviously if we are going to use this velocity of propagation measure, you need to know the distance that the velocity was, the delay was propagated within. So in here, we know that it was the last parameter, it's 2. It was 2 meters apart that the probes were inserted, probing the system. And a Cat5 is the closest that we could find on the tables for the constant that were measured that, for VOPs to represent, to be the closest to the twisted pair used in the BroadR-Reach. So if we go to this exercise, so the VOP for our example is if we insert this 0.66 constant and multiply it by speed of light, which is 3 times 10 to the power of 8 meters per second, we should get around 5 nanoseconds delay every meter of the cable for the transmission. Okay, so we had our tangled, mangled signal with full duplex communication. We'd run them through a software directional coupler, or if you happen to have hardware directional coupler, then this is what you're supposed to see on either of the probing endpoints. So now we could employ the actual decoder. So similarly to CAM decoder, you can find them under Tools in the top ribbon of PicoScope 6, selecting Serial Decoding option, clicking Create button, which should bring you the whole list of all possible, all implementation for decoders that we have in the offer for our serial decoding palette. Select BroadR-Reach, and that should bring you the end of like a configuration for this particular decoder to be set up to decode your data. So in this instance, we used math channels. So as a source for the channel should be your PAM3 signal. It could be either a coupler or the signal that you measure with the hardware coupler. Also under configuration, you've got 3 values. First 2 are the threshold, the high threshold, where all the data above this threshold should be treated as a level high, and low threshold, similarly for low. And the last option is refers to something that I haven't mentioned yet, that relates to the PHY, to actual hardware, and it relates to the scrambler. Scrambler is a little device that sits before the PHY, and it inverts the bits in a pseudo-random manner, and that's obviously for obfuscation purposes. So when you observe the data, when you inspect the transmission line, it's not obvious to the inspector, to the user, what this transmission line was carrying. So aside to the obfuscation, it also avoids a concentration of a specific frequencies within the transmitted data spectrum. And that's important because if that didn't happen, it might lead to something that is called intermodulation or cross-modulation. So it's an interference with adjacent channels that may interfere within the system, and it's not desired. So anyway, so that option, because master and slave, or receiver, transmitter and receiver, have different order of the scrambler, so the register is different, the blend of the register. So if you select master, that was the transmission coming from the master, and that's for our decoder a hint which descrambling technique order we should use underneath the hood. So we've decoded the data, and that's basically how the packet looks like in a zoomed in manner, because the payload, the very last bit, is quite long. So the first bits are the synchronization pattern, which is called preamble. It's always fixed, it's always the same. And the interesting fact about this is whenever the packet is being transmitted, because when you inspect the transmission line, you can see that the PAM3 or the obviously added together PAM3, depending whether you're probing the hardware coupler output or the Bro transmission line, you would see the signal because of the scrambler. Like it looks like it was always transmitting data, but it's not the case. So for the receiver to understand when actual transmission is happening, it's when we could see the 6 consecutive zeros, and that's from the TX enabled pin going high. And when that pin goes high, there are 6 consecutive zeros appended as part of this preamble to mark the beginning of the packet that it's being transmitted, so the other end can start listening. So okay, we've got this preamble, then we've got MAC source, MAC destination, and different other properties of the packet, which are optional depending on what was actually transmitted, but that would vary depending on the system what was actually transmitted. and the payload. So that's the graphical option. That's if you tick the box to display the adornments in the graph, the decoded adornments, this is what you would see. But there was also, similarly to Canvas, a table display. So it's the same information that they would be displayed on the graph, presented in the tabular form. So for you, so you can harvest this information or do some processing of this information for your own needs. So obviously you can hide some columns that are just not of interest to you, and just leave the ones that are important. Adjust the grid size so it is you can read it comfortably. You can filter through the table to just leave the packages that the packets that are the ones that you're interested in, and also search through them. You can apply mixed combinations of feature as you like. The other different ones as well, I'm not going to talk about them. I will leave them just for you to explore. Our software is free, so you can download it and play with it as you like, and I encourage you to do that. So that was a very short summary, very condensed. I know that there was a lot of probably new terminology. I invite you to go to use Google to learn more. It's quite interesting topic, and I must assure you that that was the most challenging decoder that we've ever built at Pico, and we will see how it goes further. But yeah, thank you very much for listening, and I'm giving back the voice to Trevor. Thank you very much.
Thank you very much, Patty. Much appreciated. So, okay, so what we're going to do now is just wrap up with a very quick, well, not that one, a very quick, yeah, thank you, Mike. So we've got now the picture on the live picture from my display on my PC, and what I'm showing to begin with, it's unfortunately the presentation speed is not keeping up anywhere near as fast as the actual speed that I can see on the screen here myself. But no matter, we'll push on. So what we're looking at here is to begin with is one signal. So it's the signal, the differential signal taken from the master device. So we've got two transceivers set up here, one as a master, one as a slave. There's a length of cable, a length of twisted pair cable between them of about 1.72 meters, and we've got each end probed differentially. So if I speed the time base up a little bit, yeah, for me now it's going quite quickly, but it's not. I can see on the presentation, we're limited by the bandwidth of the internet, I guess. So if I freeze that for a moment and just stop it, I think we can agree that attempting to resolve that as a PAM3 waveform for decoding would be pretty much impossible. We can use the rulers to look at minus a volt, plus a volt. So there are some parts of the signal that are clearly ones, some that are clearly minus ones. There's a lot in between, but the interference on the signals from the traffic going in each direction makes it impossible. It would be really difficult to distinguish whether that was really a -1 or a 0, and who knows what's happening in here. The collision of the signals in each direction is making that impossible. If I turn that on and then turn on, just for a bit of extra fun, turn on an extra channel. So now we're seeing on the same line, we're seeing the differential signal. One is captured at the master end, the other is captured at the slave end. And clearly, whether we were trying to do that in a manual fashion by eye, or whether we were trying to automate it in some way, it's pretty well impossible to see what's going on. So the last part of that then is if I just add the output of the coupler, and I'll clear a little bit of space. So this orange trace here is the output from the coupler. Run it live again. So it's with the coupler, it's much easier to see whether a signal is above or below a particular threshold, either the high threshold or the low threshold. The decoder has got something meaningful to work with once it's been processed using that software coupler. So then, just to finish up on that, this is what the decoded waveform looks like. Now, we've kind of cheated here a little bit, because in this capture, what we did, we very, very carefully and delicately, we attached some wires to the Mac device, the device I said that ordinarily you would not have access to. So in this captured waveform here, we did do exactly that. It was not an easy task. It had to be done under a powerful microscope with somebody with soldering skills and eyesight that neither of which I possess. So anyway, you can see the two waveforms here. So there is using the software coupler, we have coupled in order to look at the master to slave waveform, the slave to master waveform going the other direction, and then we've looked at the same information here on the Mac device, which typically you would not have access to. And then if I zoom in a little bit here, we can see the packet in very much the same way that that Patty just described. And there we are. There are the sequence of zeros there that start the packet, and then the preamble and the payload, and that's looking at one packet, which for looking at signal integrity problems is probably the way that you would want to look at that information. If you're looking for data errors, then the way to look at it would be to turn on the tabular readout, the table format readout, and then you can easily see what's going on line after line after line of that captured data, so that you can see in this case there are some good packets, but there are also some packets where errors have been injected, and if they don't pass the criteria, if the CRC doesn't match, or some other error condition is highlighted, then those error packets are highlighted in red. And if I double click on that one, for instance, we click there and we can go immediately to see what the packet containing that error was. More than that, it's a very similar approach to the way that Stuart showed us with the CAN bus decoding. We capture the signals, we look at the data, we correlate errors, the data errors, with signal integrity issues, and that is the essence of decoding these BroadR-Reach networks. So what I'd like to do now is just go back to the main presentation, and just to summarize a few of the things that we've seen. So, oh yes, so in the demonstration that you just saw, this was the setup. So we were using a couple of these fiber code transceivers here, and you can just about see on there some of the very delicate wiring that went onto the side of that PHY chip. So some really delicate wires that had to be attached here that wouldn't normally be possible. So these are USB powered transceivers for BroadR-Reach, with the 1.7 meters of cable in between the two. And then you can't see it there, but I can see it here, that the master was flashing with a a blue light and the slave with a green light here. And then we're using these two differential probes to probe the PAM3 signal at each end. So that was the demo setup. So you then may be asking, well, what are the hardware requirements in order to examine these BroadR-Reach signals? And the answer is that you would need a PicoScope 6000, a 6000 E-series scope. There are a few models with bandwidths from 300 to 500 megahertz, 5 gigasamples per second sampling, flexible resolution with 8, 10, or 12 bits resolution, and a massive capture memory of up to 4 gigasamples. The scope needs to be matched with a pair of differential probes. So the ones that we're recommending here would be the AD2201, 200 megahertz, or better, the AD2801, 800 megahertz differential probes. You need 2 of those. So those are the hardware requirements. And as Patty hinted, we haven't actually got a slide on the software requirements, because the software requirements are simply included with the standard issue PicoScope 6 software, and soon to come the PicoScope 7 software that our development team are working on now. So the requirements in cost terms are effectively the cost of the scope and the pair of differential probes. So to summarize then, PicoScope PC-based instruments are general purpose scopes, but they are equipped as standard with advanced features for analysis and debug of many protocols, including the ones that we've seen this afternoon. So there's 21 serial protocol decoders included currently as standard, with more in development that we will release as they come through. BroadR-Reach with the inbuilt software directional coupler, and the scopes have free updates for the lifetime of the instrument. So as we develop new capabilities, it gets incorporated into the PicoScope 6 software and is available for free of charge download for the lifetime of the instrument. I've got some pricing down here. We've got them in euros. So the entry-level PicoScope 6000 is the PicoScope 6403E. It is the 300 megahertz 4-channel fixed 8-bit resolution scope. That's a little over 4,000 euros. The AD2201 is about 1,000 euros, and you need 2 of them. And realistically, you probably would take benefit from the digital pods, so 8 digital channels. So if you want to look at that that MAC information that we showed there, that's about 600 euros there. We do have on our website a white paper on serial bus decoding. If you go into picotech.com and then into our library and look at the A to Z of PicoScopes and hit the letter B for BroadR-Reach, in that article is the link to our white paper on automotive serial buses. Sorry, it's slightly convoluted and we haven't put it on the slide here, but yeah, library, A to Z of PicoScopes, BroadR-Reach, and you'll find it there. So that concludes the webinar. We're 5 minutes or so over time, but we will at this point take any questions. So we'll have a look back. I'll have a look back now to see what. So
Trevor, I've got the questions. So thank you very much indeed for the presentation. That was brilliant, and thank you both to Patty and to Stuart for their participation as well. So that's great. So we've got 3 questions that have come in through chat. So Brian asked, when was BroadR-Reach deployed by manufacturers and who is currently using it?
Oh, I haven't got a definitive list. It's we started seeing designs for BroadR-Reach probably 4 or 5 years ago, maybe 6 years. There is a list on the web that Stuart's kindly given me, so I'll click on that list. This is the list of manufacturers that have adopted it. It's pretty wide. So we're seeing BMW, Hyundai. Well, actually, this is a mix of vehicle manufacturers and ECU manufacturers. So BMW, Broadcom, of course, as the originators of the standard, Freescale, Harman, which make the in-car infotainment systems, Hyundai, NXP, STM Microelectronics, and more. So that's the start. There are many others. The Tesla, of course, most of the Tesla models are built around BroadR-Reach. There are many others, but I think a search of the web would reveal more than I can reel off the top of my head.
Okay, wonderful. Thank you, Trevor. So the second question, there's a fourth question that's just come in as well. The second question came in from Ari, and this might be one for Patty to answer. It says, can the waveform decoding do continuous capture, in brackets log all messages, or are there dead times between acquisitions?
So in our scope, in our software, PicoScope 6 and 7 uses, and also SDK, uses 2 different modes. One is called block mode, and the other one is streaming. So block mode captures a block of data and displays them on the screen, and then another block of data and displays them on the screen. Whereas streaming just streams continuously the number of samples over and prints them on the screen as it goes, as the acquisition, as the buffer is being filled with the samples. So it is possible. So there are like 2 questions in one. So it is possible to capture continuous signals, and whether it is possible to decode them. Yes. So it's all boiling down to because our software is run on the PC, so it depends on your PC strength, how powerful is your machine, because there's a lot of computation, calculations, power needed. So what is advisable usually is, if you're interested in the streamed data, in the one continuous block of data, so you should capture the data first, stop the capture, either using single trigger, for instance, so it automatically stops it and just captures one big block of data, and then apply the post processing of any kind, whether it's a coupler or whether it's a BroadR-Reach decoder or any decoder, any post-processing in general. So that way, like, you're not hammering your PC power so much. But yes, so it is possible, but depends on your PC strength, power.
Okay, wonderful. Thank you, Patty. And another question also from Ari. Can the logging show both directions of communication separated and marked, e.g. master stroke slave? I can take that one as well. So unfortunately, all of our decoders only output one information stream. So obviously here with the coupler, you are trying to untangle two-way communication. So you've got 2 signals, but the output is always one. So in order to get the information coming from both directions, you unfortunately would need to set up the coupler twice, reversing the arguments. So it can run the coupler in the reverse direction, and that way you can set up the decoder around the coupler output. So it is possible, but unfortunately you would need to set it up separately because of our architecture. This is how we designed it before, and this is how we keep it consistent.
If I can add something there, Patty. So it was what in fact was going on in the signal that I was showing. I was looking at both the communication in both directions. It just happened that the packet that I captured was master to slave, and the slave to master packet was somewhere far away. But it you know, as Patty says, by setting up 2 decoders, one for each direction, it will put it on the screen.
Absolutely, and it's applicable not only to BroadR-Reach, to any decoder. So if you happen to have multiple signals and that would require multiple decoders, you can set up multiple decoders and observe them on the screen as the communication goes on.
Okay, wonderful. Thank you, Patty. I'm going to answer, there's some more questions come in. I'm going to answer them slightly out of sync because there's 3 that I can answer reasonably quickly. And then there's 2 more for our technical team in the office. So a question from Steve, where will we be able to see the replay? So the replay is hosted via Live Webinar, and Live Webinar use Amazon servers, but we will also be putting the video up on YouTube. So we'll make sure that everybody gets the recording link as soon as possible. A question from Alan, which says, who is your target market for this? Surely not workshop techs. No, this is not an automotive application for use in a garage. This is very much designed for people who are looking at R&D or design and development for future cars. So, or modifications to existing cars. So this is very much a test and measurement application, but aimed at automotive manufacturers or designers or people working in the automotive space, as opposed to people actually working in garages. And a question from Christian, which says, is it possible to decode BroadR-Reach with a 5444D 200 megahertz PicoScope, or do you need one of the 6000E scopes? And the answer to that, as Trevor touched on earlier in the presentation, is you do need a 6000 series scope for the bandwidth and for the memory depth that this decode requires. So 2 more questions for our panel of experts, please. So John asks, what are typical bandwidth requirements for oscilloscopes in the automotive space? Trevor, perhaps you'd like to take that one?
Yes, thank you. It relates really to the previous answer. So 300 megahertz is the minimum bandwidth, and but it needs to be backed with a decent sampling speed as well to get a good single shot capability. So it works fine with our 6403E, so 300 megahertz and 5 gigasamples per second sampling captures the waveform nicely, but not below that. So the 5444D previously mentioned, it's got 200 megahertz bandwidth, but a sampling speed of a gigasample per second. That doesn't hack it.
Okay, wonderful, thank you. Another question from Ari, saying, is there a difference between 100 base T1 and BroadR-Reach? And if there is, can this setup be used for both?
It's the same thing.
It's the same thing. Thank you. Okay, that's good. And then a question from Sven, who says, great presentation, thank you. And again, thank you to the team. Any plans to incorporate more debugging functionality into PicoScope, like what I've seen with the Warwick software demo? I'm not aware of vendor you mentioned during the presentation that is using 5444D, but I'll look at their offerings. As an owner of PicoScope hardware and doing a bit of CAN debugging, I'd like to see some of their functionality in these programs in PicoScope. I think we would need to understand a little bit more about what the Warwick software demo incorporates. But Sven, if you'd like to get in touch with us offline, then you'd be most welcome. I'll send you my email address in the chat. That's perhaps something we can pick up offline.
Could I jump in a little bit there as well, Mike? So
please do.
Just to say that we do work pretty closely with a few other vendors. So we are aware of Warwick, but we have a very close partnership with Vector Informatic that produce the Canoe suite of debug tools that is used for looking at other layers in the stack. So for looking at protocol analysis on automotive buses, CAN traditionally, but increasingly now BroadR-Reach. So they have adopted the 5444D as their scope. So if you want to look at the waveforms that are underneath the protocol analysis that they're doing, then we are very familiar with that particular solution.
Okay, wonderful. Thank you very much indeed, Trevor. There's a couple of other people typing, so we'll hold on for a couple more minutes if there are other questions coming through. So Edwin says, thank you, well done. And Sven says also, thank you for answering. So that's an absolute pleasure. And I put my email address into the chat. So if anybody has any offline questions, please feel free to forward them to me, and I'll make sure that they reach the right people. Ari says, thank you for all this info. I've been debugging systems like this and expect to do some 100-base T1 in the future, but probably intercepting the CPU stroke MAC points, not yet the cable. So Patty, any comments on that?
Not really. I don't know. I've been sorry. I didn't understand that there was a question.
I think that what Ari's saying is he's looking at doing some BroadR-Reach decoding, but intercepting the CPU-MAC points, not yet the cable. So I suspect that's perhaps a slightly different twist on it. And again, Ari, please feel free to reach out if you've got more questions. And if you're looking to do BroadR-Reach decoding in the future, obviously we'd be delighted if you were to buy a PicoScope 6000E with which to do it. So Simon says, does the amount of twist in the wire affect the propagation velocity?
Oh, that's a very technical question. I don't think it does.
Thinking back to my college days, I think it does a little bit, but most twisted pair cables come off the reel. They look like that, and a little bit more or a little bit less, it won't make enough difference to upset the coupler.
Okay, wonderful. Thank you both. I think that is
exactly
that's the last question we've had come in. In fact, Simon says thank you very much. And his question related to beyond measurable limits. So I think
that's right.
Yeah, I think we've addressed that. So with that, I will declare the meeting closed, or the webinar closed, and just thank you once again to everybody who's attended. I hope you found that useful. And thanks again very much indeed to our panel, for Trevor for essentially presenting the core of the information, and to Patty and to Stuart for their contributions. So thank you very much indeed, everybody.